Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through problem set 19, mixtures of gases and partial pressures. Number 1A says, what is meant by standard temperature and pressure? These are the numbers that you'll want to know for standard temperature and pressure. They are consistent for gases, okay? You'll notice that STP, when we deal with other things, that the STP in different concepts is actually different. But for the sake of gases, it's 273 Kelvin, which, if you remember, is 0 degrees Celsius, okay? And it's actually 100,000 pascals. A lot of people are like, well, wait a minute, wouldn't it be 101,325, which is the generic conversion of pascals to atmospheres? Well, the thing is that 1 bar is actually the standard for pressure, and it's not quite 1 atmosphere. They're slightly different. It's a little bit greater than an atmosphere, but the actual standard pressure for all gas situations is going to be 1 bar or 100,000 pascals flat. Okay. Letter B says, what is the volume of 1 mole of an ideal gas at STP? And does it matter what gas? And that is 22.4 liters, okay, is equal to 1 mole of an ideal gas. Now, I'm going to put 1 mole of X because it does not matter. Does not matter what gas it is. Any gas, any ideal gas, excuse me, right here, any gas that is considered ideal is going to have the same volume, just even for every mole that it has at STP. Okay, it's going to be the same for every gas. So anytime that it's given you a situation where it says, okay, gas X and gas Y are at STP, and there's 1 mole of each, what volume do you expect each of them to take up? Doesn't even matter what size difference there are between them. Even if gas Y weighs more than gas X, they're going to take up the same volume. All right, number 2, birds and sailplanes take advantage of thermals, rising columns of warm air, to gain altitude with less effort than usual. Why does warm air rise? Well, warm air is lighter, okay? It's lighter, and so it's easier to rise with the warm air because it's already moving upward. And the reason it's moving upward is because the higher you go in the atmosphere, the less dense the air becomes. Okay, that's why in Utah, for example, at a higher altitude, we actually have it's actually 0.95 atmospheres instead of 1, which you normally find at sea level. Okay, because as you rise, the overall atmospheric pressure decreases because the density of the air actually decreases as well. Okay, and so warm air is going to rise to the less dense region because it wants to spread out, right? Warm air is moving faster, has more kinetic energy than, let's say, cooler air, where the gas particles, yeah, they're moving, but not quite as fast, and that makes them a little bit more packed together, whereas warm air is lighter and will push upward. It's kind of, think of it like a balloon, right? Balloons, especially when they're filled with helium, they're trying to rise, they're trying to expand their gases, and so it ends up rising because the pressure on the inside of a helium balloon is actually a lot less than the pressure on the outside, and so it's the pressure coming from the air on the outside pushes the balloon upward, okay, to less dense areas. So that's why warm air rises, is because of density. Okay, density of gases is going to be one of the main topics that we cover in this problem set. Okay, so with that, we'll go to number 3 here. It says, what is the density, okay, in grams per liter of sulfur hexafluoride at 350 degrees Celsius and 1.55 atmospheres of pressure? Okay, so first of all, if we look at the Pivnert equation, we actually have, there's a derivative equation, an equation that we derive from the Pivnert equation that can help us solve for density. Now, if you remember, density is equal to mass over volume, right? The mass spread over an area, which is, in this case, our volume. And in this case, what we're going to do in order to get density in here, if you remember that moles, okay, moles is equal to little m, okay, in grams, over big M, which is in grams per mole. Okay, because if you cancel that, you end up getting moles here. So because of that, I can actually solve for, I put this in here for N in the Pivnert equation, and then I have an M, and I already have a volume here, and if I can just get them to, get them in this designation, I can actually solve for a density. So I'm going to plug this in. PV is equal to now M over big M RT. Okay, and so what I'm going to do here is I'm going to move everything that's except for the little m over to this side, and then move volume over here algebraically. So that would look like PM over RT is equal to M over V. Okay, you're welcome to try that out on your own with the algebra, but just trust me on this. This is what it's going to look like. And then we get M over V, which is obviously density. And so I'm actually just going to put in equals D now, equals D. And this was in mass in grams, and the volume was in liters. Volume was in liters. So here we've got density in grams per liters. And then this is now our equation. This is going to be pressure times the molar mass. If you remember, the molar mass is in grams per mole, and then the R constant, and then temperature, which obviously is in Kelvin. So with this equation now, PM over RT, I'm going to solve this for sulfur hexafluoride. Now I need the pressure, which is 1.55 atmospheres in this case. Okay, and then the molar mass of sulfur hexafluoride is about 146 grams per mole. Okay. And then that would be over the R constant, which we know is 0.0820, we'll say 6. And then I'm not going to put all the units there just for room's sake, but you know that it's liter atmospheres over mole Kelvin. And then overall, we need this temperature to be in Kelvin, which is about 623 Kelvin. So I'm going to put 623 Kelvin. And then you just plug and chug from here. And if you do this right, you should get about 4.4 grams per 4.43 grams per liter for the density of this substance. So ultimately, this equation is, I think it may be on your equation sheet, but even if it's not, you can actually derive it from the ideal gas law to solve for a density, and you'll be using that a lot throughout this problem set and on the next test. All right, number 4 here. I'm going to give myself a little bit more room here with the writing here, but it says, what is meant by the partial pressure of a gas? Basically, all it is the pressure that each gas contributes to a sample. So pressure each gas contributes, and I'll just put contributes. So any time that you have a mixture of gases, there is going to be an overall pressure, but each gas, depending on how much of that gas there is, will make up some portion of the overall pressure in that gas sample. So in part B, here's an example. It says a gas mixture contains 7 grams of N2, 2 grams of H2, and 16 grams of CH4. What is the mole fraction of H2 in the mixture? Now, the reason that they're asking you what the mole fraction is because this is one piece of the equation in finding an overall partial pressure. So we'll use that when we get to number 6 here, when we determine actual partial pressures. But overall, the partial pressure really is dependent on the mole fraction, meaning however many moles of my gas, moles of X gas X, right, over the total amount of moles, okay, that's going to be my mole fraction. Okay, we use that the symbol chi for that. For the mole fraction, okay? And overall, the partial pressure of a gas, so partial pressure, this is what partial pressure, I'll just put maybe G, of a gas is going to be the P total, the total pressure times the mole fraction, okay? Times the mole fraction. So that's why it's super important. We can have the whole pressure, but if we don't know how many moles of each compound we have in there, we can never find out the partial pressure that each gas will contribute. So what we need to do then is find out what the molar masses of these substances are, and then use that to find how many moles there are of each, and then take each one over the total. So in this case, I got 7 grams of N2. Okay, now remember N2 is made up of 2 nitrogens, which are each I'm going to say 2 times 14 grams. So that's going to be 7 grams of N2 is equal to 28 grams of N2 over 1 mole. Okay, so that's going to be what? 0.25, right? That's going to be 0.25 moles of N2 that are present in this sample. Then I've got 2 grams of H2, 2 grams of H2, which is about how much 1 mole of it is. So there's going to be about 1 mole of H2 here. And then lastly, I've got 16 grams of CH4, and then I've got 1 mole. If you count that up, it is about 16 grams per mole for CH4 as well. So that's also one mole of H2, or sorry, CH4, my bad. So overall, I only have one piece of the puzzle so far. I can add all of these up, okay, and that would give me the total moles. In this case, obviously, that's going to be 2.25 total moles. So now I'm going to erase this stuff and then use this information to now find mole fractions of each thing. So now I'm going to take 2.25 moles of N2, N2 over 2.25, and then I'm going to take 1 mole over 2.25, and I'm going to count that as both H2 slash CH4. Don't get confused by that. I'm just, because they're the same, each one is 1 mole, I'm just going to consider each one's fraction as that, okay? So overall, what you should get is about 0.11 up here for N2. Okay, so that's the mole fraction for N2. And then 0.44 for both H2 and then 0.44 for CH4. Okay, so that would be overall the mole fraction. This is the number that you would actually plug in. But if you think about it, these are percentages, right? So this would be 11%. N2. So the gas sample by moles is 11% N2, and then 44% H2 and 44% CH4. So those are the mole fractions. And then if they had given us the total pressure, we could actually find the partial pressure of each gas by multiplying each of these mole fractions by the total pressure. Okay. Number 5 will actually have us do that. So letter A says a glass container with a volume of 4.21 liters holds 0.12 grams of Cl2 gas and 0.145 grams of F2 gas at a total pressure of 2 atmospheres. Okay, determine the partial pressure of each of the gases. So remember that P of the gas, the partial pressure of the gas, is going to be the P total, the total pressure, times the mole fraction of each gas. Okay, and then the mole fraction is the moles of that gas. Okay, over total moles. So what we have to do is turn each of these values into moles of those substances, and then find the mole fraction for each, multiply it by the total pressure. So in this case, I'm going to take 1.20 grams of Cl2 and turn it into its number of moles, which in this case, we've got 70.90 grams per 1 mole of Cl2. And then we've got 1.145 grams of F2. Okay, and that ends up being about 38 grams of F2 for every mole of F2. Okay, here I get about 3.82 times 10 to the negative 3 moles of F2. And then for the chlorine, I get about 1.69 times 10 to the negative 3 moles of Cl2. Now, what I have to do is add these together, okay, add them together. So I'm going to add them and then get the total moles, which if you do that correctly, you should get about 5.51 times 10 to the negative 3 moles. And then take each of these and divide them by 5.51 times 10 to the negative 3. 5.51 times 10 to the negative 3. And if you do that, you should get about 0.307 for the chlorine and about 0.693 for the fluorine. Okay, remember, these are just fractionless values, or unitless values, I should say. This 0.307, these are like 30.7%, right? And then this would be like 69.3% sort of thing, right? But in order to find the partial pressure of each gas, right, I got to multiply each of those mole fractions by the total pressure for. So for the, we'll start with the fluorine. Okay, the partial pressure for fluorine is going to be the total pressure, which is 2 atmospheres, times its mole fraction, which we found was 0.693. And then that same thing for chlorine would be 2 atmospheres times 0.307. Okay. For the first one, you should get about 1.386, and this would be what atmospheres, and this would be specific to F2. Okay, specific to F2. And notice that it correlates a lot with the number of moles that are there. So the higher the mole count for any particular substance, the higher the partial pressure will be for that substance. So and then you should get about 0.614 atmospheres. And then if you were to add these up, these should add together to get 2 atmospheres, right? Because they're just fractions. These were each fractions of an overall total. So all right, so that's mixtures of gases and partial pressures. I hope that was helpful.